Let's talk light. As artists, this is probably one of the most applicable sections out of the physics that we've talked about. And so we're going to spend time talking about what light is and some of the properties of light. So first, what is light? At the base of all of it, it is transverse waves. So remember, those are the waves that go up and down as they go forward. And they are created by electromagnetic fields. So we've talked about electricity in the past. And so electricity is electric fields caused by charges, and magnetic fields are just created by magnets. Well, what we didn't get a chance to talk about is that electric charges, when they move, create magnetic fields. And magnetic fields, when they move, create electric current. And so light is the interaction between these two. So as the waves for light travel, you've got moving electric fields that generate magnetic fields. Those magnetic fields generate electric fields, and so on. So that's why these are electromagnetic waves, basically. So they just keep generating themselves as they travel with this interaction between electric fields from charges and magnetic fields created by those electric charges, electric fields moving. The thing that we call light is the visible portion of the electromagnetic frequencies. So we're going to see there's an electromagnetic spectrum. It's huge, and light makes up a very small fraction of it. So this is the part that we can actually see. It travels almost 1,000,000 times faster than sound in air. So this is why if you've noticed that you can see lightning and then hear the thunder, that's why, because light is going to travel much, much faster in air than sound will. So let's take a look at the electromagnetic spectrum. So I told you, like I said, it's a very tiny part, the visible part that we call light of the electromagnetic spectrum. So we go all the way from short wavelengths, high frequency gamma rays, all the way down to the other end with low frequency, long wavelength radio waves. So these guys, they are waves, so they have the same sort of properties as sound waves. So we've got wavelengths, from crest to crest or trough to trough. We've got frequency, how fast those waves basically are moving, so how often those wavelengths come through. And as we go from one end of the spectrum to the other, so as we go from radio waves up to gamma rays, the energy increases. And the same is true when we go through visible light. As we go from red up to violet, we go from lower energy to higher energy, because those wavelengths are getting closer together, so higher in frequency, and the wavelengths are going to get shorter. So the other parts of the electromagnetic spectrum, you're probably familiar with some of these. So radio waves we talked about when we talked about sound. Microwaves, we use these for heating, well, mostly heating. There's some other functions for them as well, but you're most familiar with them to use to heat up food. Infrared. So infrared's not far from the red part of the visible part of the spectrum. Infrared is also known as heat. So we've already talked about the infrared part of the electromagnetic spectrum. So it has some energy, but not as much energy as the rest of this spectrum. The visible part that we're going to focus on for the majority of this chapter, ultraviolet, is just above the visible spectrum. This packs some energy. This is the part that we have to protect ourselves from, as far as the light coming from the sun. In fact, the part of the light, or the part of the electromagnetic spectrum that's coming from the sun, is pretty much all infrared through ultraviolet. There's not really much of any of the rest of this coming from the sun. Then we keep going. We've got X-rays, which we use in order to do diagnosis and so forth. But we're going to be using some pretty powerful radioactive material in order to do that. And then we've got gamma rays, which are, as you can see, very short wavelength, very high frequency, very high energy waves coming from other parts in the galaxy that can do quite a bit of damage if they hit living tissue. They don't do it often though, so don't panic about it. Like I said, though, we're going to be focusing here on the visible part of the spectrum. You probably know it as Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. So we're going to be looking at different aspects of light, just like we did with sound, different characteristics. So the first one that I want to take a look at is reflection of light. So we saw reflection in sound. So light bounces just like sound does because they're both waves. So when light encounters a surface, there's some different options. It can reflect, it can refract, it can be absorbed, or it can be transmitted. And so we're going to look first at reflection. So reflection can happen a couple different ways. What we're looking at here is what we call the law of reflection. The law of reflection only applies when you have an absolutely smooth reflective surface. So things like mirrors apply with the law of reflection, or like you see here, very smooth water surface. But it's an interesting phenomenon that happens with reflection of light. So the law of reflection says that when light comes in and hits one of these flat surfaces, you'll also hear them called plane surfaces, P-L-A-N-E, for flat. When it hits one of these flat, shiny surfaces, the incident ray or the incoming light ray, when it hits, it's going to hit the surface and be reflected or bounced off at the same exact angle that it came in at, just in the opposite direction. And so this is why when you get something like this, like a mountain in a lake, it looks like the mountain is completely upside down in the lake to you, because those light rays are bouncing off the lake to you off of every point of that mountain in exactly the same spots, so that it reverses the image in the water. And so they're basically bouncing off in reverse, but in the same angles. So it makes that image appear exactly the same, just in reverse. And that's what we've got going on here. This also allows for the creation of what we call virtual images. So let's take a look at some image formation. So what is a real image versus a virtual image? So a real image is located where the light is. So what are we talking about? This would be like movie images on a screen, or for example, if you're watching this on your laptop or your phone, this video. So the light is on your screen. That is the real image. Or, if you're watching, instructor project things onto a screen from a projector. The light is there. You can put your hand between the light and where it's being projected. That is a real image. A virtual image, on the other hand, is going to be created by reflected light. So the example of a virtual image is like what you can see here in this mirror. So it's going to have the same size as an object formed behind a mirror. So it's going to look like it's behind that reflective surface. And it's going to be located at the same position where the reflected rays appear to converge. So let's see what I'm talking about here. We take a look at this picture. So we've got this box sitting in front of the mirror on your side, right? So the light rays come and hit the box, and they hit the mirror off of the box. So they're bouncing to the mirror. Because of the law of reflection, those rays are going to hit your eyes at exactly the same angle, just in the opposite direction. But what will appear to happen is that that box will appear to be behind the mirror, and this is the extended ray part, the same distance behind the mirror that box is sitting in front of the mirror. So why is this? It's a result of our eyes and our brains interpreting the information that we're getting from the light. We know that object is not behind the mirror, right? But the light rays are pointing at us in such a way that our brain is like, well, no, the light is coming from this direction, so the object has to be back here. We know that it's not behind the mirror, but that's why it appears to be behind the mirror, because our eyes and our brain are extending that light, not interpreting it as it's bouncing, but extending it backwards, because that's the way light should travel. Light should travel in a straight line.